Well, hey everyone, and welcome back. A lot of the videos I've been doing previously or recently have been on folding, so I figured, you know what, let's take a step back to one of the principal concepts of structural and applied geology, which is our favorite little topographic profile. Now, a while back, I think it was a couple weeks, maybe even a month at this point, I did two videos on how to convert between a topographic profile and a cross-sectional diagram. And that's one of the most basic things you can do with a topographic profile to really give you an understanding of what the land is doing here. But another one of the most basic ones that you'll find to be really useful is calculating the slope between 2 points anywhere on this map. Now, slope should hopefully ring a bell from mathematics, simple algebra, right? If you've got a linear function or a straight line, to calculate the slope of that, you just take your vertical change or your change along the y-axis, divide that by your change along the x-axis, and you'll get a general idea for what your line is doing in terms of how steeply it's sloping. Obviously, a steeper slope is indicated by a greater value for your slope indicates a steeper line, because that means you have more y displacement proportional to x displacement. So just thinking about that mathematical concept of slope is really helpful for what we talk about in geology, because it really is the same thing, just sort of applying what we usually see only on coordinate planes or simple functions, or graphs of functions, and applying it to the real world when we're dealing with horizontal displacement and vertical displacement. So I've drawn out here just a sample topographic profile. Nothing too detailed, but we've got some lines in here. These are our contour lines. All of them are labeled. They don't have to be, but we're going by 20s here. We can see some gradual decrease. I hope you can read these numbers, but we go down from 100 to 80 to 60 and so on until we reach 20, at which point, after a while, we see this steep increase from 40 all the way up to 140. Then there's another big gap in between representing a much more gradual incline until we get to 160, and that's the last line we see on this. Now we've also got this scale up here and this compass, just to give you an idea of, just to make it feel more like it's in the actual world, you know, put an actual measurement on it and let us know that, hey, north is up. Pretty typical of a map. And then finally, and most importantly, we have our line XY. And if you watched my video on converting between topographic profiles and cross-sectional diagrams, you know that this is going to be our line of interest. Although in this case it doesn't necessarily have to be, I thought it would be useful just for this first example of finding slope that I'll walk you through. So the first piece is we're just going to find the slope of line XY. Now, of course, the first thing we should do is just define what is slope. So we'll represent slope with the letter M, just sticking with mathematics, or the mathematical variable we use for it. But instead of saying x over y, I think it's better to think of it as, or excuse me, instead of y over x, I think it's better to think of it as delta v over delta h, which is to say your vertical displacement or your change in vertical position divided by your change in horizontal position. Don't mistake that for delta v, or don't mistake delta v for a change in velocity. I can assure you kinematics has nothing to do with this. Okay, well, given that equation, we can just jump right in and first start with the easier one that we can get just by reading this map on its own, which is delta v. So delta v, we have our units here. We have x and y, and x appears to be somewhere starting between, once again, I hope you can see this, between the 80 and 100 contour line. In fact, it appears to be halfway between the two in terms of its distance. So obviously we don't know the exact position. If you were that determined in a real life situation, you could actually find that exact point on the map, go there and take a measurement as far as how high you are above sea level. But for the sake of this example, it should be correct enough for us to round to about 90 meters. And yeah, we're using meters this time instead of feet or inches. I decided I wasn't going to be a bully to non-American audiences. But actually, I did mess that up. Since we're going from y, since it's xy, we're assuming we're going to start from x and go to y. So just to be more correct, we would start with y and say, well, this appears to be just a bit above 160, so it probably hasn't reached anything. It probably hasn't reached 165 or 170 yet. So we'll round our y position to 160 meters vertically. Now we can subtract our 90 meters vertically that we had at our x position. So we get that our vertical displacement is 70 meters. Now the only other piece to find is delta h, or our change in horizontal position, which we can find using this scale here. I have 200 meters represented by 2 inches, so we can just measure the length of this line here real quick. That is about 11.5 inches total. So we can write that as 11.5 multiplied by 200. Well, actually, if 2 inches represents 200 meters, we just multiply it by 100, which of course gets us 1,150 meters. So our slope can therefore be represented as delta V 70 divided by delta H 1,150. And that's all there is to it. So just by looking at these 2 points, x and y, on their own, we can say that it's a very gradual but upward slope. And obviously this is ineffective if we wanted the exact specifics of what's going on in between these 2 points, right? Because obviously at this point the slope is between x and this point A I've labeled here, the slope is negative, because you're getting a sort of gradual decrease. Meanwhile, between say the 40 and the 140 contour lines, it's probably a lot greater than 70 divided by 1,150, because we see a much more condensed, the lines are much more condensed, implying that our vertical elevation is increasing much more rapidly. So that's why I put in these extra points here. So the next thing we can do is, just as another example, find the slope of line segment AB. So A and B are right here. It's sort of at the beginning of this rapid increase, not quite in the heart of it, I think. I think it ends a bit early. We really see the biggest change vertically compared to horizontally in this small region here. But we'll see how this compares to our slope of xy. Remember, this is on the same line too. So we'll see exactly how it compares. Let's start by finding our delta V. Well, B is on the 60 contour line, so we can say that that is 60, and A lies on the 20 meter contour line. 60 minus 20, our vertical change is 40 meters, and that is positive because we are going upwards. And then our horizontal difference is going to be, this is about 2.5 inches, so it's about 1.5 times 200, which of course, simple mental math, that is about 300 meters. So our slope now is 40 over 300. Now obviously, just because of the way I drew this, and I made the horizontal scale maybe a bit too big, or a bit too, how should I say it? I scaled it down a bit too much perhaps. But you can just tell by comparison, 40 over 300 versus 70 over, what was it, 1,150, right? if you just look at these two proportionally, this is much greater than that. Because if you look 40, well, we don't even increase that by twofold in order to get to 70. Meanwhile, 300 we've practically increased fourfold in order to get to 1,150. So this one is comparatively much more of a gradual, less steep slope. And we can tell that just by looking at the numbers. So, just for one final example, I figured it would be good to get off this line of xy and take a look at another example that I just provided 2 points for. So that is the slope of CD. So, first things first, calculate our delta V. Delta V is going to be 160, that's where D is, or that's the contour line it is on, minus C appears to be on the 40 contour line. So that's 160 minus 40. That's going to be 120 meters different vertically. Delta H is going to be our quick little measurement. Just put that there. That appears to be about 8 inches even, estimating a bit. So if for every 2 inches we have 200 meters, then that's 4 times 200. So our horizontal change is going to be 800 meters. So finally, M is going to be 120 over 800. Just a final little example, and this does once again account for this more rapid period of change. So same profile, several different values for M. You could calculate them between any given 2 points on this diagram here. But yeah, that's one of the most basic things, one of the most useful things you can do just for getting an idea of the land and how steeply certain rocks are sloping, which in turn can be used to calculate dip angles. So it's an incredibly useful thing to know, pretty simple if you know algebra. So hopefully this was a pretty easy video to grasp, and hopefully it was informative, otherwise good review. Hope you guys enjoyed, and I will see you all in the next video. Ciao!